everyone. Now, we will learn the basic knowledge of the boiler steam and water system and equipment. This section of knowledge points is as follows. First, boiler steam and water system and its function. Second, steam drummer. Third, downcomer pipe. Fourth, header. Fifth, water-cooled wall. Sixth, superheater and reheater. Seventh, economizer. The boiler steam and water system refers to an organic whole composed of devices such as the economizer, steam drum, downcomer pipe, water-cooled wall, superheater, reheater, header, desuperheater, and their connecting pipes and accessories. The function of the boiler steam and water system is to effectively absorb the heat released from the combustion of fuel and to heat the feed water entering the boiler into superheated steam with a certain pressure. Next, let's get to know the steam and water systems of natural circulation boilers. First, circulation boilers and one-slope boilers.
The green line represents water, illustrating the steam-water flow process within the boiler. Water under a certain pressure first enters the economizer of the boiler, where it absorbs heat released from the flue gas in the flue. Then, it enters the steam drum of the boiler. From there, the water flows down through the downcomer pipes into the water-cooled walls, arranged around the boiler furnace. Here, the water absorbs heat, begins to vaporize, and produces steam. The resulting steam-water mixture naturally rises and returns to the steam drum. The steam drum separates the steam from the water. The separated water returns through the downcomer pipes back to the water-cooled walls, where it absorbs heat and vaporizes again. The steam separated in the steam drum enters the superheater, where it is further heated to increase its temperature. This superheated steam is then sent to the steam turbine to perform work. The steam exiting the superheater and entering the steam turbine is known as main steam. For a 300 megawatt unit, the main steam pressure can reach up to 16 MPa, approximately over 160 atmospheres, and the temperature can exceed 530 degrees Celsius. The steam, after performing some work in the steam turbine, experiences a decrease in both temperature and pressure. This steam needs to be returned to the boiler's reheater for further heating. Once the temperature reaches over 530 degrees Celsius, it is sent back to the steam turbine to continue performing work. The purpose of returning steam to the boiler for reheating is primarily to improve the efficiency of the power unit. The steam, after performing work, is condensed back into water and returned to the boiler. This type of boiler is known as a natural circulation boiler. Its characteristic is that water continuously vaporizes in the water-cooled walls to produce steam. Because the density of the steam-water mixture is less than that of water, it naturally rises into the steam drum. The water separated from the steam will naturally flow back into the water-cooled walls through the downcomer pipes. Therefore, this circulation method is called natural circulation. When the main steam pressure is higher, the density difference between the steam and water becomes smaller, and it is necessary to use a forced circulation pump to generate power, to drive the working fluid to flow in the water-cooled walls. This type of boiler is called a forced circulation boiler. When the main steam pressure is further increased, 600, such as in hyperammeter units, like 600 megawatts, a so-called once-through boiler must be used. This type of boiler does not have a steam drum, and the working fluid passes through the water-cooled walls only once. At the outlet of the water-cooled walls, it is already all steam, and thus there is no circulation. The basic form of the water-cooled walls in a once-through boiler is a horizontal spiral tube arrangement.
The steam drummer is a long cylindrical pressure vessel made of steam plates, including the bellow body and the end caps. Next, the structure of steam drum.
The steam drum, also known as the boiler drum, is a cylindrical container made by welding steel plates together. It is composed of two main parts, the barrel body and the heads. On the upper part of the steam drum, there are pipe connections for saturated steam, self-use steam, safety valves, risers, balance containers, continuous blowdown pipes, dosing pipes, water-cooled downcomers, concentrated downcomers, emergency drain pipes, water level gauge connection pipes, feedwater pipes, and recirculation connections. The ends of the steam drum are sealed with heads made by stamping steel plates and welding them onto the barrel body. There are manholes on the heads, and the manhole baffles are tightened from the inside to the outside of the steam drum with screws. Inside the steam drum, there are devices such as cyclone separators, louver separators, perforated plates, cleaning hole plates, continuous blowdown pipes, dosing tanks, feedwater pipes, and emergency drain pipes. The cyclone separator consists of a barrel body, an inlet pipe, a top cap, a copper bottom guide plate, and an overflow ring. To maintain the stability of the water level in the steam drum, the steam water separator employs a staggered arrangement of left-handed and right-handed configurations. This is to prevent the formation of vortices at the inlet of the downcomer, which could otherwise cause the downcomer to carry gas. At the entrance of the downcomer, a cross baffle is installed.
Then, the working process of the steam drum.
The steam-water mixture first enters the connecting box and then, along the tangential direction, enters the built-in cyclone separator. For steam-water separation, the separated water is let out through a copper bottom and enters the water space. The separated steam rises and passes through the top cap of the vertical corrugated plate separator, entering the effective separation space of the steam drum. The preliminarily separated steam then uniformly ascends from below through an upperlaid balanced plate type steam cleaning device for bubble cleaning. The cleaned steam is finally passed through a top perforated plate for further separation before being uniformly drawn out from the steam drum.
Modern large-scale power plant boilers widely adopt large-diameter central Duncomber pipes. It is drawn out from the lower part of the steam drum, vertically arranged to the bottom of the furnace, and connected through its lower end to small-diameter distribution water branch pipes that connect to the lower headers of the water-cooled walls. The Duncomber pipe continuously supplies water from the steam drum through the lower header to the water-cooled walls to maintain the normal water circulation. To ensure the reliability of the water circulation, Duncomber pipes are all arranged outside the furnace and are not heated. In the boiler, a cylindrical pressure vessel that connects many identical and parallel arranged pipes is called a header or collector box, primarily used for gathering, mix, and redistributing the working fluid. Headers are generally arranged outside the furnace and are not heated. Most headers are made of seamless steam pipes with a larger diameter and the same material as the heating surfaces, with end caps welded on both ends, forming a barrier wall with multiple tube sockets for connecting pipes. In the boiler, the water-cooled wall is an evaporation heating surface composed of many barrier tubes. In the boiler, generally arranged around the inner walls of the furnace, or partially in the middle of the furnace, the working fluid in the water-cooled wall moves upward while receiving the heat from the high-temperature flame radiation in the furnace, and the heat transferred by the high-temperature flue gas, turning into steam. The functions of the water-cooled wall are as follows. First, heat absorption and steam production. Second, protecting the furnace wall to prevent slugging of the furnace wall. Third, enhancing heat transfer and saving steel. Below is the structure of the membrane water-cooled wall.
The membrane water wall, which is predominantly composed of smooth tubes, or internal ribbed tubes, is either pressed or welded together with fins. This particular welded fin tube membrane water wall consists of internal ribbed tubes with a diameter of 38.1 mm and a thickness of 7.5 mm, welded together with flat steel of 9 mm thickness. To prevent or delay the occurrence of heat transfer deterioration, certain water wall tubes employ internal ribbed tubes. These internal ribbed tubes feature single or multi-start helical grooves on their inner walls.
The superheater and reheater are two important heating surfaces of power station boilers, and also components in the thermal power plants used to improve the thermal efficiency of the steam power cycle. In the boiler, the superheater and reheater are arranged in the upper part of the furnace, and in the vertical flow ducts at the tail end. The superheater is used to heat saturated steam into superheated steam with a certain temperature, and through operation regulation, ensure that the steam temperature at the outlet of the superheater is within the allowable range. The heater is used to heat the exhaust steam from the high-pressure cylinder of the steam turbine into reheated steam with a certain temperature, and through operation regulation, ensure that the steam temperature at the outlet of the heater is within the allowable range. According to different modes of heat transfer, the superheater can be divided into convection superheater, radiation superheater, and semi-radiation superheater, 3 types. This is an example of the structure of the low-temperature superheater.
The low-temperature superheater is arranged at the upper part of the rear vertical flue duct and belongs to the convection-type superheater. It consists of an inlet header, horizontal serpentine tube sections, vertical tube sections, and an outlet header. The main body is composed of 4 sets of horizontally arranged serpentine tubes, each set containing 84 rows, with each row of serpentine tubes consisting of 5 tubes connected in parallel in a multi-loop structure. The vertically arranged tube sections are suspended from the rear roof, hanging the horizontal serpentine tube sections on the outlet header.
This is an example of the structure of the cladding wall superheater.
The platen superheater is arranged on the sidewalls and bottom of the horizontal flue, as well as on the front and rear walls and sidewalls of the rear flue duct. It is composed of the platen superheater on the rear wall of the rear flue duct, the platen superheater on the front wall of the rear flue duct, the platen superheater on the left sidewall of the rear flue duct, and the platen superheater on the right sidewall of the rear flue duct. The platen superheater adopts a membrane wall structure, which ensures the airtightness of the boiler.
This is an example of the structure of the rear screen superheater.
The rear bottle superheater is arranged at the furnace outlet after the separation bottle and belongs to a semi-radiant type superheater. Consists of 22 panels. Each panel formed by 20 parallel tubes U, bent into a U shape in a loop structure.
According to the different modes of the heat transfer, the reheater can also be divided into convection reheater, radiation reheater, and semi-radiation reheater, 3 types. This is an example of the structure of the high-temperature reheater.
The high-temperature heat carrier is composed of an inlet header, an outlet header, and U-shaped tubes. The inlet and outlet headers are positioned above the horizontal flue outside. The U-shaped tubes are vertically arranged inside the horizontal flue, with 98 panels of tubes arranged along the width direction of the flue, 10, each panel consisting of 10 tubes U twisted into a U shape.
The economizer is a type of heat exchanger equipment that uses the flue gas from the boiler's tail flue to heat the boiler feed water. Its main functions include, first, absorbing the heat from the lower temperature flue gas to reduce the exhaust gas temperature, decreasing the heat loss with the exhaust gas and saving fuel. Second, since the feed water is preheated in the economizer before entering the steam drum, this reduces the amount of heat the feed water absorbs in the heating surfaces, allowing the economizer to replace some of the more expensive evaporation heating surfaces, thereby lowering the cost of the boiler. Third, raising the temperature of the feed water to reduce the temperature differences across the steam drum wall, decreasing the corresponding thermal stress and extending the service life of the steam drum. Economizers are classified according to the state of the working fluid, and their outlet into boiling type and non-boiling type. In boiling economizers, the working fluid at the outlet reaches the saturation temperature, while in non-boiling economizers, the outlet water temperature has not yet reached the saturation temperature corresponding its pressure. Economizers can also be categorized by the material used into cast iron type and steam tube type. This is the structure of the steam tube economizer.
This is a common suspension-type steel tube. Used in large boilers, the economizer. It is made up of many parallel serpentine seamless steel tubes, along with an inlet header, an intermediate header, and an outlet header. This is the inlet header of the economizer, composed of a 559 mm diameter closed tube section, which is the feedwater inlet pipe joint, and the serpentine tube joint. This is the intermediate header of the economizer, consisting of a 324 mm diameter closed tube section and the serpentine tube joint. The serpentine tubes are the heating elements of the economizer, made by bending seamless steel tubes. With an outer diameter of 28 to 51 mm, the material is typically 20G carbon steel. This is the outlet header of the economizer, composed of a 406 mm diameter closed tube section, which is the feedwater outlet pipe joint, and the serpentine tube joint. This is a staggered arrangement of tube banks, which has the advantage of being easy to clean with soot blowers and simple for suspension.
This is the structure of the cast iron economizer.
Cast iron economizers are commonly used in boilers with low pressure and less stringent water quality requirements. A cast iron economizer consists of individual cast iron tubes with square fins on the outside, connected through 180-degree elbows. The structure of the cast iron economizer includes a cast iron connection elbow for the water inlet of the economizer, a cast iron fin tube for the water outlet of the economizer, and the economizer is arranged in the boiler's tail flue. Water enters the economizer horizontally from one end of the bottom row of tubes, flows back and forth to the other end, and then enters the next row of tubes above. This flow continues from bottom to top, while the flue gas flows downward from above, brushing against the tubes. In a countercurrent heat exchange.
Classmates, in this section, we have studied the boiler steam and water system and its functions, including the steam drum, non-common pipes, heaters, water cool walls, superheaters, reheaters, and economizers. These pieces of knowledge are all related to the safe operation of the boiler. Today, we have finished introducing the content regarding the boiler steam and water system and the equipment. Thank you all.